So in this video, we're going to use the squeeze theorem that we talked about last time to actually prove an important trig limit. And it's one that without the squeeze theorem, we wouldn't really have a way to prove it. We might be able to look at it graphically or numerically to get a good idea about it, which would be certainly a valid thing to do. But if we notice, if I take a look at trying to evaluate this limit as theta goes to 0 of sine theta over theta. So if I was to try to evaluate that, well, I would try my direct substitution, sine 0, but sine 0 is 0 divided by 0, and we know that is an indeterminate form. We also don't have any, like trig identities or anything I could really use on this. I mean, it's just sine of theta. And so, there's nothing else I can do with that. So this is where the squeeze theorem is going to come into play. So first of all, we have a little graph here, and we have the unit circle, so at the origin center with a radius of 1. And so one thing I want you to recall from your trig days, of course, everything we do is going to be based on radians. In fact, this formula for the area of a sector is really based on theta being in radians. So in calculus, if I haven't said this yet, make sure your calculator is in radian mode and leave it there. Everything we do is based on radians. So you might remember from your trig days, there's a formula for the area of a sector, which is 1/2 theta r squared. You may or may not remember that. Oftentimes I forget things like that, and I have to think about what the area of a circle is, pi r squared. And I think, okay, wait, pi, that's actually half of the full angle. So then it's like, oh yeah, that's a 1/2 theta r squared. So that's a formula for the area of that green region, the area of that sector. Now, what we can then say is, okay, the area of this sector is certainly going to be greater than or equal to the area of the inscribed triangle that you see on the left, and it's going to be less than or equal to the circumscribed triangle that you see on the right. So when you look at this one over here, I'm really talking about the area of this some of the colors. I don't know what happened when I downloaded these images. Some of these colors don't look very good. So we're talking about the area. This is the circumscribed triangle. And so that's language we'll use at the end of the semester again. So the triangle that's kind of giving us an overestimate, it's drawn outside of the function. And then over here, the inscribed triangle is this one right here in yellow. So let me just do a little better job of shading that in. So this is the inscribed triangle. So certainly my area of the sector is going to be in between these two values. So I think we can kind of all agree on that. All right, so let's think about what we know about the area of a triangle then. So area of a triangle is just 1/2 base times height. We already have our formula for the area of the sector. And so when we think about the unit circle, so what I want you to think about on that area of the inscribed triangle, so we're thinking about, again, this is my base of this triangle, and of course this is the height of this triangle. Well, it just so happens, if this is my angle theta here, so this is my angle theta, kind of got shaded over, this base and height is going to be the xy values of this point on the unit circle, which I say it that way because it may help kind of jog our memories a little bit here. So when you think about the unit circle, so you think about maybe what you did in trig, how you developed the unit circle, when you think about the xy points at any point on the unit circle, you learned how those were giving you the cosine of that theta and the sine of that theta. So you learned that that was giving you the cosine of theta is the x-coordinate and the sine of theta was the y-coordinates. And so that is our base and our height. So this is our base, so this is cosine theta, and then our height here that's our sine theta. Which again, this makes sense. What is this really? This is going back to your right triangle trig, right? So this is just going to be, since we have a radius of 1 here, you know, cosine is just simply your adjacent, which is the base side over the hypotenuse. And then your sine of theta is your opposite side, which in this case is the height of the triangle over the hypotenuse. So basic right triangle trig, think about what you know about the unit circle from your trigonometry days, and pretty quickly, hopefully, that all rings somewhat of a bell. And so what we get is that our base is cosine theta and that our height is sine of theta. All right, continuing, again, we know that this is the unit circle, so the area of this sector, anywhere you go, the radius here is 1. And then as we move over to the right-hand side, so once again, what we have here, so this is my, again, radius of my circle, that's going to be 1. And so that 1, of course, is equal to the base of this right triangle. Now, the height then, so we also, of course, need its height. So this is our base. And then we also need our height. Well, again, tangent of, let's rewrite this theta. It got a little bit shaded over here. So if you think about, you're trying to find, this is our height. And so when you think in terms of theta, in this picture, you know the base this time is 1. And so you're looking for a relationship between looking at theta, it's the side opposite is your height, and your base you know to be 1. So here's what we know. We know that our tangent of theta is your opposite over adjacent. So that's going to be, so this is just your basic opposite over adjacent, right? So what we know is that our tangent of theta is going to be your height that you're looking for over 1. So your height is simply equal to tangent of theta. So that's the height of that circumscribed triangle. All right, I'd say we're in pretty good shape here. So we're just going to rewrite kind of everything we have here. So I have my cosine of theta and sine of theta here. This was equal to 1 squared, which is 1. And then I'm going to rewrite tangent as sine theta over cosine theta. All right, so continuing, what we're going to do here, I'd like you to kind of, first of all, before we go any further, think about what is our kind of goal in all of this. I should have said this a little bit earlier, but we're trying to get the ratio of sine theta over theta sandwiched in between something, right? This is the limit I'm trying to determine, is sine theta over theta. So I'm trying to figure out this limit as theta goes to 0. So I'm trying to get sine theta over theta kind of in the center here. And so right now I have a theta, that looks good, but I'd like to get rid of the 2. And I'd also like to get sine in here somehow. Now, if I notice, I have sine in the outermost functions here, but it's in the numerator. So here's what we're going to do. We're going to kind of get rid of this 2 by multiplying everything by 2. And then in order just to kind of get some form of sine in there, since these two sines on the outermost functions are in the numerator, initially I'm just going to divide through by sine. So I won't have theta over sine theta. I'm sorry, I will have theta over sine theta. So I'll have its reciprocal. So there is a little bit of, maybe kind of logic behind what we're doing here. But essentially for this proof, I don't expect that you're going to know this or be able to, reproduce it on your own. But I do expect that you can kind of follow along. And certainly you will have questions in your homework about using Squeeze theorem. All right, so here we go. We're multiplying everything through by our 2 over sine of theta. And so as we do that, on the far left then, we are going to have, it looks like just a cosine theta as we multiply that through. And then in the center here, it looks like that's just going to give us theta over sine theta. And then on the far right, looks like we're going to have our 1 over cosine of theta. And so when you take reciprocals, you reverse inequalities. So working with an inequality, if 1 is less than 2, and I take that reciprocal, that means that 1, well, let's do, instead of 1, let's say 2 is less than 3. Its reciprocal, though, 1/3 is less than 1/2. So you have to reverse the inequalities. So in essence, if we were to do that, so if I take, let's write out one extra step in here. So if I take the reciprocals, because that's what I'm really going for in the center here is sine theta over theta, then I take the reverse of those inequalities. Now let's just rewrite this. Instead of going from greatest to least, let's rewrite this same inequality that I just wrote from the perspective of least to greatest. Let's do cosine of theta is then less than or equal to sine theta over theta is less than or equal to 1 over cosine theta. All right, so basically we're here. Now if we take the limit as theta goes to 0, we can evaluate this limit because on the far left, I'm just going to have cosine of 0. So that's going to be 1 is less than or equal to the limit as theta goes to 0 of sine theta over theta is less than or equal to, and this is going to be 1 divided by cosine of 0, which is still going to be 1. And so therefore, by Squeeze theorem, then this is going to tell us that the limit as theta goes to 0 of sine theta over theta is equal to 1. And you also have kind of a graph showing that visual Squeeze theorem taking place there. So on the right-hand side, when you look at this graph, this is the function. So this is 1 over cosine theta. And then this function here, this is just the function of cosine theta. And so the function that you have being squeezed in the middle, that is your sine theta over theta. So this is your sine theta over theta function there. All right, so this is one you're going to want to have memorized. Once we've proved it, you want to be able to use it. Now, the next thing we're going to talk about here is a quick corollary to this theorem. So we have really kind of two important theorems, or the first one's a theorem, the second one's a corollary, two important trig limits, let's say. So again, if I look at this limit as theta goes to 0 of cosine theta minus 1 over theta, if I was trying to evaluate this one by hand, you know, pretty quick mentally, we're going to see that cosine of 0 is 1 minus 1. And so, of course, I'm ending up with 0 being divided by 0. That's indeterminate. So what we're going to do here, in order to prove this one, we're actually going to do something that you might think back to a previous section that you're encouraged to do sometimes with radical functions. And we often do this when we have a binomial of like cosine theta minus 1, because it's going to eventually invoke one of our Pythagorean identities. So we are going to multiply by the conjugate of cosine theta plus 1. And so when we do that, in our numerator, when you would multiply that out, you're going to have cosine theta times cosine theta would be our cosine squared theta. And then, of course, you're going to have, and I don't expect that you would write this out. I would hope, in fact, you wouldn't need to, that your plus cosine theta and your minus cosine theta are gone. And then you just have minus 1. Now, that's in our numerator. And, of course, we have theta over the quantity of cosine theta plus 1. Okay. Now, what I want you to be thinking about then, and this is a trig identity that I would think that you should be familiar with. It's the most common form of your three forms of your Pythagorean identity. You should know that sine squared theta plus cosine squared theta is equal to 1. So if you subtract 1 on both sides here, Well, that's going to give you your cosine squared theta minus 1, but that's going to mean that you're also going to need to subtract the sine squared over to the other side. So what am I trying to do here? I'm just trying to get the cosine squared theta minus 1, because that's what I have in this numerator. So on the left-hand side, I have my cosine squared theta minus 1, and on the right-hand side then, I have minus sine squared theta. So sine squared theta plus cosine squared theta equals 1 is rewritten as cosine squared theta minus 1 equals minus sine squared theta. So in my numerator here, cosine squared theta minus 1, that is equal to, this is equal to minus sine squared theta. Now, if at this point you were to attempt to try direct substitution, you'd still get 0 over 0. But what I want you to be seeing, this is why this is a corollary to the theorem, is we're going to be using the sine theta over theta limit that we just proved. So what I want you to be noticing is, oh wait, maybe since, and this is really key, it's not just any limit involving sine theta over theta. It has to be the limit as theta goes to 0 of sine theta over theta. So I see some of that in here. So what do I see in particular? I see that I have a sine theta squared, and so that's like sine theta times sine theta, and yeah, there's a negative factor there. And in the denominator, I have a theta times this other binomial. Well, when you multiply fractions, all you do is multiply numerators and multiply denominators. So you can kind of break up any of these factors any which way you want. So I could write one factor as sine theta over theta. I could write, and again, I need a negative somewhere, I'm just going to put it here. And then the other one could be negative sine theta over my cosine theta plus 1. I mean, so kind of check this for yourself. What happens when you multiply these two fractions back? Oh yeah, I get negative sine squared theta over theta times that binomial. So one of our properties of limits says that the limit of a product is equal to the product of the limits. So I can take, well, I can factor that negative all the way out in front. Constant multiples get carried along. I'll leave it on the inside though, I think, for now. So limit as theta goes to 0 of sine theta over theta times the limit as theta goes to 0 of negative sine theta divided by cosine theta plus 1. And again, because this is the limit as theta goes to 0, this is the one that we just proved. So by our above proof, by the squeeze theorem, we know that that is equal to 1. And then on the second factor, that limit, we can just use direct substitution. So sine of 0 is 0, and then cosine of 0 is 1, 1 plus 1. So you'd have 0 over 2, so that's just going to be 0. So we end up with 1 times 0, which is equal to 0. So here's where we're going to end this video with our second really important, and after this point you can just apply it, trig limit. So we had from the original limit as theta goes to 0 of sine theta over theta. So we proved that one with good old squeeze theorem. So this was equal to 1. So that we proved by our squeeze theorem. And then now, by the above proof, this is often called a corollary of that. So this one, the limit as theta goes to 0, corollary, I don't know why that doesn't look right, by corollary of, I'll just say above. That's the one we just proved. Another way you'll often see this one written is they will reverse the order of the subtraction, factor out a negative, and you're still going to have a negative 1 times 0 would still be 0. So that means that you can equivalently write this as 1 minus cosine theta, because again, factor out a negative, you have the original one, negative 1 times 0 would still be 0. So these two are the two common ways you see this corollary written. All right, so these are our kind of special trig limits, I would say, that kind of require this squeeze theorem proof. And we're going to be using these, just like we did in the last example, really, as they come up periodically within the context of other problems. We're going to have to kind of work on some of the specifics and how we develop these in terms of their use. There's some things we have to work on here. So when we come back next time, we're just going to look at a whole slew of examples that involve limits of trig functions. We'll also throw in some log functions and things like that as well. So next time we come back, we're going to look at a lot of examples.